All right, in this last example, I've got two rational functions that I'm comparing. One is greater than the other. Now, if I plotted the graph of each rational function, you'd have vertical asymptotes, x-intercepts, and they'd be crossing at various places. And so to compare this is quite difficult. What I'd like to do, like normal, is to get 0 on one side, get a single rational function on the other side. The solutions to that final rational inequality will be equivalent to the solutions in this original rational inequality. All right, so we're going to do that by creating a 0, and of course I like to use it on the right side, but again it won't matter really. If I subtract this rational function from both sides, I will end up with 5 over x minus 3 minus 3 over x plus 1 is greater than 0. Okay, I've just subtracted the entire fraction over. Now, they have different denominators. I need to get a common denominator here. So in the first fraction, I'm going to multiply the top and bottom by x plus 1. And in the second fraction, I'm going to multiply the top and the bottom by x minus 3. Okay, that will create the LCD of x plus 1 times x minus 3. Now on the numerators, I'm going to distribute. So I get 5x plus 5 over the LCD, x plus 1 times x minus 3. Here, I'd have, again, distributing the 3, I'd have 3x minus 9 over x plus 1 and x minus 3, which is then greater than 0. Okay? So I want to subtract these two fractions. Again, distributing the negative will change both signs. I'll do this kind of in one step rather than writing it out twice. 5x minus 3x is going to be 2x. 5 minus negative 9, that's really 5 plus 9, that's 14. And then on the bottom, I still have x plus 1 and x minus 3 greater than 0. Now in the numerator, I have a common factor of 2. I can factor that also. So let's do 2 times x plus 7 all over x plus 1 times x minus 3, and we'll make that greater than 0. Okay, so there's my new rational inequality. It's fully factored, which is nice. And so the solutions for this new inequality will be equivalent to the solutions to the original inequality. This one I can compare a single rational function to 0 rather than two rational functions to each other, which is quite a bit more difficult. So, again, to solve this, I need the zeros of the numerator and denominator. The zeros of the numerator, well, there's one of them. So on top, the 0 would be x equal negative 7, and that's going to be an x-intercept. Okay. Zeros of the denominator, we'll call it the bottom. I don't always like doing that, but I'm saving some time from writing. Would be negative 1 and positive 3. Okay, setting those equal to 0 and solving. And those are both going to be vertical asymptotes. Again, because there's no shared 0, there's no holes. Okay, so I'll just write that over to the side. No holes. So now I have 3 points to consider as endpoints to my sign chart. Negative 7 is on the left, negative 1 is toward the middle, and 3 is to the right. Okay. My vertical asymptotes, I always put a dashed line, and my x-intercept, I always put a solid. Okay. Now in this one, this inequality, it really doesn't matter whether we're looking at vertical asymptotes or x-intercepts because my original inequality has no equal sign in it. So the endpoints are not going to be included either way. So no matter what, I'm using parentheses and no brackets. But I still like to have that in there just for consistency's sake. So now I start plugging in numbers. And I'm gonna go to the left interval here. Let's try maybe a -10. In the middle here, maybe a -2 would work. This one, maybe a 0. I like 0 whenever it's included. And then over on the right here, maybe I put a 5 or something. You know, I don't know. I'm just picking some things I think are nice. Again, you can pick whatever you want as long as it's in the interval. Try to make the arithmetic work well for you. Okay, let's try the -10. Again, I want to go back to my final rational inequality, not the original here. I'm just trying to pick out whether the function is positive or negative. The 2, remember that a constant or a positive value will not change the answer, so I really don't need to even consider that the 2 is there. I'm really looking for the sign of the other 3 factors and comparing those, because the positive 2 won't change the sign. So when I plug in the -10, -10 plus 7 is a negative number, so it's a negative on top. On the bottom, -10 plus 1. -10 plus 1 is a negative number also. I don't know why that took me a moment. And -10 minus 3 is also negative. So all 3 factors are negative. 3 negatives make a negative. And so, that. And so every output in that first interval will be negative. Now I try the -2. Put in -2, -2 plus 7. Well, the positive is dominant there, so that's going to be a positive on top. -2 plus 1 is negative, and -2 minus 3 is also negative. 2 negatives make a positive, so every output in that second interval will be positive. And then 0, plug in 0. That gives me a positive on top. 0 plus 1 is positive. 0 minus 3 is negative. I get positive over a negative, which is negative, 1 negative. And then finally the 5, plug that in. 5 plus 7 is positive. 5 plus 1 is positive. 5 minus 3 is also positive. Everything is positive, makes it positive. Okay. So now using my sign chart, I can see I want values that are positive, right, greater than 0. And there are 2 such intervals, the second and fourth. Okay. So my final answer, final solution, will be all x values in the interval from -7 to -1, union with 3 to infinity. Those are my 2 intervals with positive value outputs. Again, I'm not including any of the endpoints because, well, 2 of them are vertical asymptotes, but the other one, even the x-axis or the x-intercept, is not included because we're not using an equal sign here. So I don't really care where it's equal to 0. I just want positive or greater than 0. Okay, so 2 intervals will work. Any number that you plug in from one of these 2 intervals will solve the original rational inequality.